Okay, after discussing about adversarial search in general, now we'll discuss about optimal decisions in games. In a normal search problem, the solution is just a sequence of actions that leads to a goal, but in adversarial search, things change. So Max, let's say, is the person who plays the first move in a game, and Min is the opposition or the adversary against whom Max plays. In a normal search problem, the solution is just a sequence of actions, like I said, and that leads to a goal. Adversarial search, how it changes? Max cannot simply plan a path. It must consider how Min will respond. So instead of a fixed path, Max needs a strategy, a complete plan that specifies the best move in every possible situation, no matter how Min responds. But we always assume Min responds optimally. So Max finds a contingent strategy specifying Max's move in the initial state, then Max's move in the states resulting from every possible response by Min, then again Max's moves in the states resulting from every possible response by Min to those moves, and in that way. The goal is to find the optimal strategy, one that guarantees the best possible outcome, assuming the opponent also plays optimally, as I already said. So this is an example to illustrate. We consider this example game tree. This is also called a one-ply game tree. It's basically one move by Max, followed by one move by Min, and then the outcomes. We did not consider the full game tree because it can be very large, as we have already said. Max is represented with an upward triangle and Min with a downward triangle. And the terminal node shows the utility values for Max, remember. So Max wants to maximize its utility, while Min wants to minimize Max's utility. That's the important thing. Now here, Max can choose among moves A1, A2, and A3. For each move, Min responds with B1, B2, and B3. And the game ends. The utility values at the leaves range from 2 to 14. 2 is the minimum, 14 is the maximum. If Max plays by himself, he will definitely choose the maximum utility, which is 14. But there is an opposition, an adversary, which is Min, and the objective of Min is to minimize Max's utility gain. So Min will want Max not to go anywhere over 2. So that's important to understand. Now, how do we decide what Max should do? This is where the Minimax principle comes in. The Minimax principle. Okay? So let's go back to this where we are talking about the optimal strategy. We are saying the Minimax value of a node is the utility that Max can guarantee from that state, assuming both sides play perfectly or optimally. If the state is a terminal state, it just returns its utility. We have already seen in this that if it's a terminal state, we already know the utility. Like in the chess, once you have gone to the last stage, you know somebody is won or lost. But you don't know the utility value is somewhere in the middle. So we have no idea about the utility in the middle. So we have to go down to the leaf level to know what utility we gained. So if we are at the terminal state or the leaf state, whatever the utility, that's the final value. Otherwise, if it's Max's turn, choose the move with the maximum minimax value. Okay, if it's Max's turn, then you choose the move with the maximum minimax value. Otherwise, if it's Min's turn, then choose the move with the minimum minimax value. That's exactly this thing says. In this example tree, we have shown Min nodes back up their lowest child value and Max nodes choose the highest among them. Okay, Min nodes back up the lowest child value. So Min will choose among this, whichever be the lowest, like 3 among these 3 nodes. And Max will choose whichever be the maximum among its children. So that's the way it works. So how the Minimax algorithm works? So that's what we want to know. This is the Minimax algorithm. So basically, implements the recursive definition we have just shown. You start at the root, recursively compute the minimax down to the leaves. Okay, you down to the leaves. You go down recursively until you have reached to the leaf level, and then you get the actual utility value. If terminal state, you get the utility. And then you back up the values level by level until the root decision is clear. So you back up from bottom to top. Okay, it's basically runs a DFS. So like example, at node, let's say min does what? These are the 3 children, and the utilities produced are 3, 12, and 8. Min will choose among them whichever is the minimum, which is 3, because this is min's turn. It will never allow max to choose 12. It will play optimally, so that means the max's benefit reduces to 3. Similarly, so min for this node it chooses 3, for this node it chooses 2, and for this node it chooses 2, the minimum. Now max finds out among these 3 what is the maximum, because min is playing optimally. So max will get 3 because 3 is the maximum among this. So this guarantee guarantees optimal play against an optimal opponent. Okay, if min cannot play optimally, then max might get something more than 3. But 3 is guaranteed, even if min plays optimally. If min messed up somewhere at some step, you can get more than 3, up to 14. So that means max's root best move is as A1. So if you go to A1, then this is the path to the optimal value, which is 3. Okay, so this is the path, A1 and then B1. So now, what is the complexity of the Minimax algorithm? If the branching factor is B and the maximum depth is M for the tree, then the time complexity is order of B to the power M. Space complexity is order of B time M if all actions are generated at once. And O of M if generated one at a time. Okay, depth first. For real games like chess, B to the power M is an astronomically large number. So Minimax alone is impractical. But it forms the foundation for more efficient methods like alpha-beta pruning, which can help you to reduce some states and then make Minimax viable for games like chess.